Okay, in this example, we are going to use the function f of x equals 1 over x to complete the table below and then graph the function. The purpose of this example is to actually examine the new parent function 1 over x, which is the reciprocal function. So to go through it, we're just going to replace our x value, or our x in the equation, with each of our x's here. So for f of -3, we're going to replace x with -3. So it's 1 over -3, which as a decimal is -0.3 repeated, which might be a little easier for some to graph. So I'll probably write it as -0.3 repeated here. Next would be the -2, doing the same thing. F of -2, just replacing x with -2, which would approximately get, actually would exactly get -0.5. -0.5. Same thing with the -1. F of -1, just replacing x with -1, which will give us -1. Then 1/2, so now we're on to the fraction. So f of -1/2, which would be 1 over -1/2. And when you're dividing fractions, you want to do keep, change, flip. So keep the first fraction, change the multiplication, and flip the second fraction over, which multiplies and becomes -2 overall. This is called the reciprocal function, which is a good indicator that it might flip the fractions, because that's what the reciprocal actually is just flipping the denominator and numerator in the fraction. And then we have f of -1/3, which is going to end up doing the same thing, 1 over -1/3, which will flip the fraction, resulting in overall -3. Now the next one is one of my favorites. I always love this one. It's so fun. And I always get like a bunch of different answers whenever I do this in class. But 1 over 0. If you try to do 1 over 0, you can't actually do it. It's actually undefined. So we can't actually graph this because there's no actual value for it. And then moving on to the other ones, they would be essentially a mirror image of the left side of the table, except everything's positive. So the 1/3 would be 3, the y value would be 3, y value for 1/2 will be 2, y value for the 1 will be 1, then 0.5 or 1/2, and then 0.3 repeated or 1/3. So we've gotten all the values in the table with the exception of the one that we can't actually find at 0. So if I plot all my points, we have -3, -0.3. We got -2, -0.5, -1, -1, -1/2, -2, and -1/3, and -3. And then the next side, we have the 1/3, 3, 1/2, 2, 1, 1, and 2, 0.5, and 3, 1/3. You can kind of see that we have this kind of almost like elbow macaroni shape going on in quadrant 1 and quadrant 3 of the coordinate plane. But you can see we kind of just gloss over this. And no matter what values I pick, I could extend this to picking something even closer to 0. I could pick like 1/8, which is even closer. It's not actually going to reach the x-axis. In fact, I don't have, there it is. If I pull up Desmos here, you're going to see that if I type it in and zoom in, 1 over x. So you can see that there is a gap right there. And if I zoom correctly, I can make it even bigger. No matter how far I zoom out or how far I pinch the axes down, if I can actually grab them, no matter how far I zoom out here, there's always going to be a gap, assuming I can actually grab the axes and get it to zoom out so that you can actually see it. the gap just gets smaller and smaller as we go farther or closer and closer to x of 0. So you can see that gap. You can see the scaling on the axes has it so small right now for the x-axis, but we are so massively up there for the y-axis. So what ends up happening along the y-axis and actually along the x-axis as well is we get these lines called asymptotes, which my graph is actually approaching but will never actually get to. I like to describe them as the annoying sibling of the math world, because remembering back in car trips, just sticking your finger in your sibling's face and going, "I'm not touching you," driving them crazy. But that's kind of what's going on here. The graph is getting closer and closer to these asymptotes, but it's just kind of taunting it, going, "I'm not touching you," because it never actually gets to the asymptotes. So when you draw it in, it's essentially hug the asymptote, curve in through the points, and then hug the asymptote without ever actually touching the asymptote. And then same thing on the other one, hug the asymptote, curve in through the points, and then hug the asymptote. So when we go on to the next example, we're going to be using some properties of this basic parent function, 1 over x, to help us graph using transformations, which is a lot easier than plotting a bunch of points. We'll use our two asymptotes, the horizontal asymptote, y equal to 0, the vertical asymptote, x equals 0, and to get a little bit more of the shape in, we're also going to use two of the points, and the 2 points that I recommend using are the ones that are actually whole values, the 1, 1, and -1, -1. You can actually use any point, but those are the easiest because they're whole numbers. It's easier to deal with. And just the vocab that we talked about. So asymptote, the parent function for reciprocal function, its equation. It has two asymptotes, x equals 0 and y equals 0. And its domain and range, it exists everywhere except for where those asymptotes are. Yeah. Okay, in this example, we're going to graph the function y equals -2 over x minus 2. And we have off to the side the plus 1. We're going to also state the equations for the asymptotes, and then state the domain and range. So going through this, I'm going to use the same rules I usually use. Inside affects x and opposite for transformations, and outside affects the y values, and in the same way. Inside in this type of function means inside with x, like it always does. X is in the bottom in this type of function, bottom of the fraction. Therefore, if there is something in the bottom of the fraction with x, it affects it when we apply our transformation rules. So I see x minus 2 in the bottom of the fraction. Therefore, inside affects the x values, but in the opposite way. So it's going to actually have an effect of adding 2 to the x values. Now for the y stuff, most people can easily recognize the plus 1 as being outside after going over the fact that stuff in the bottom is for x. However, this 2 is also for the outside, for the y values. If we go back up, normally this function should have a 1 on top. Notice we have the -2. The way you write fractions, though, or the way you multiply fractions, it can also be written as -2 times 1 over x minus 2. Because when you multiply fractions, you simply multiply the top and then multiply the bottom. So -2 as a fraction will be -2 over 1. So you would do -2 times 1, getting the -2, and then 1 times the x minus 2, giving you the x minus 2. So the -2 on top also goes for the y values. So our transformation rule for y is we're going to take our y values and multiply by -2 and then add 1. With the rules being written out, we're ready to start trying to graph it. So we'll take some information from the basic pairing function. We'll take those two ordered pairs that are nice whole numbers to make it easier to deal with as reference points. So we're going to use 1, 1 and -1, -1 from the parent function, as well as the two asymptotes, x equals 0 and y equals 0. From here, we'll apply our transformation rules to each of these key points and key ideas for the function 1 over x. Like I've done in the past, I'm going to go through and do all my x stuff first, and then I'll go back and do the y stuff. My rule for x is to add 2 to my x values. So my first order pair will add 2 to the x value. 1 plus 2 is 3. Second one, -1 plus 2 is +1. And then we also have to do it for the asymptote as well. So we'll have x equals, if we add 2 to our value for our asymptote, we are going to get 2. Now for the y stuff, we're going to multiply by -2 and then add 1. So 1 times -2 is -2, plus 1 is -1. -1 times -2 is +2, then plus 1 is 3. Then we also have our asymptote. So we'll multiply 0 by -2, which is 0, plus 1 is 1. So now that we have all this information, we're going to go ahead and use it on the graph. I'm going to start by graphing my asymptotes. X equals 2 is my first asymptote. This is a vertical line where all my x values are 2. And since it's an asymptote, it's not actually part of what we're trying to graph. So we reference it with a dotted line because it's not actually points that our function is taking on. It's more of just a reference line, so we know what it's approaching, but doesn't actually pass by this point. And the same thing with y equals 1. It's a horizontal line, though, where all the y values are 1. Again, because it's an asymptote, we tend to represent it with a dotted line, or I guess a dashed line as well. Then we have our 2 points to plot on here. We got 3, -1, and we got 1, 3. Remember, if they are on the asymptotes, then something is wrong, as well as whenever you're doing this for specifically the reciprocal function, they should never be like side by side. So you can see that there's kind of a giant plus sign formed by the two asymptotes. They will always be across from each other, diagonal from each other in those. So either where they are now or diagonal this way. They should never be side by side or right above each other in the whole little plus sign that's formed by the asymptotes. But once we have all this information, we just have to draw our graph in. So to draw it in, we hug along the asymptote, curve in through the point, and then hug the other asymptote. Hug the asymptote, curve in through the point, and then hug the asymptote as best as we can. So we have graphed the equation, which was one of the things that we were asked for. We were asked for 3 things. Graph the equation was 1. The second thing was state the equations for the asymptotes. Well, we've actually already done that as we were using our transformation rules. So these are the equations for the asymptotes. The last thing we need to do is state domain and range. Domain and range at this point is pretty easy because for reciprocal functions, the domain and range is always all real numbers except for where the asymptotes are. So the domain is all real numbers. I'm going to use the funny R for the real number symbol. But we cannot have, or x cannot equal 2, because we have the x asymptote at 2. And similarly for range, it's going to be all real numbers. But we cannot include 1 in that because we have the asymptote, which means it can't take on that value. And there we go.